My name is Tom Shirless, and I'm the president of Carnegie Mellon University's RoboSub team, Tartan AUV. Tartan AUV is a small team comprised of about 8 active members spread across the software, mechanical, and electrical disciplines. CMU has a long history of presence in the robotics industry, and Tartan AUV provides yet another way for undergrads to get exposure to the industry, especially the marine robotics industry. This year, we undertook a bold redesign and are ready to introduce our second ever vehicle, Kingfisher. Kingfisher has been redesigned from the ground up to support more compute power, more sensing, and a fully overhauled software stack. We're proud of what we've achieved in the past year, and we're ready to show it to you guys.
Our sub gets its name from the elusive kingfisher bird, which dives underwater to catch fish to eat.
JFK to LAX, my mics get checked. Coast to coast, I rock it most times, no sweat. Me to you, get what we do, but never forget. Now's the time, fall out of line and take your first step. Feet, 5, 4, fun. I smell hip hop and I want some.
Hi, my name is Joy Soden. I'm a rising junior studying mechanical engineering. This is my first year on Tartan AUV as part of the mechanical team. I've mostly worked on designing housing for the IMU and camera, also referred to as the slam box. As a second-year team, Tartan AUV's driving goal was to create an AUV that's sustainable for the future. Last year was a great learning experience for us and heavily impacted our strategy for this year. One of the biggest learnings was to focus on excelling in a few tasks instead of trying to complete all of them at once. Therefore, we set out to build a strong base for the AUV along with rigorous testing on all fronts: mechanical, electrical, and software. The electrical and mechanical team focused on designing a versatile AUV, which can be improved and adjusted to run in future competition. Meanwhile, the software team focused on developing a generalized autonomy stack to move away from a per-task hard-coded stack. We wanted to make it easy for new members to contribute and also develop generalized autonomy algorithms that can be leveraged for multiple tasks.
I'm Joey Wood, and I'm the mechanical lead for Tartan AUV. This year, I led the design of our brand new vehicle, Kingfisher. This year, we went with a dual hull system with a mid-cap at the center. This allows us to separate out power and battery electronics from what will be compute and perception electronics. The sub can do roll, pitch, and yaw maneuvers as well as motion on all 3 linear axes. Last year, for our submarine Albatross, we relied heavily on consumer off-the-shelf parts. This year for Kingfisher, we invested heavily into custom CNC machining, as well as water jet and 3D printed parts in aluminum, steel, and a variety of plastics. Undergirding the sub is a rigid steel weldment that holds all vibration-sensitive perception hardware, such as the Doppler velocity log, the IMU, the sonar, and the stereo cameras. The steel weldment also provides a rigid backbone to support our rib cage frame. To open the rib cage, you simply need to access these 4 screws on the top of the vehicle. The folding rib cage allows for a sleeker and more compact design during dive configuration, but also minimal obstruction during servicing configuration.
Sweet.
We undertook such a radical redesign this year because we anticipate that the sub will be used for many years to come. Modular mounting points and a spacious electronics enclosure allow for an expansion of internal systems in future years, such as new sensors and new actuators.
Electrically, Kingfisher takes a lot from its predecessor Albatross, but improves in a few very significant areas. We've isolated our logic and actuator power supplies, meaning we no longer have things like camera outages if an actuator floods or is overloaded. We've upgraded from an NVIDIA Jetson TX2 to an AGX Xavier. This gives us more compute power, allowing us to upgrade from a single monocular camera to a total of 2 pairs of stereo cameras, one front-facing and one downward-facing. This means 4 video streams simultaneously. We've replaced the Pixhawk flight controller we used last year with an Xsense MTI 200 IMU. This IMU features very high-performance MEMS gyroscopes, as well as a high degree of immunity to magnetic distortion, which is very present at the Transdeck facility. This magnetic distortion led to significant problems with our navigation systems last year, and it's something we were very determined to set out and fix with Kingfisher. The most significant upgrade to our sensory package is the addition of a Teledyne Pathfinder Doppler velocity log. The DVL provides feedback on our linear velocities, and when fused with our IMU measurements, allows precise 3D localization of the vehicle. For communication with the sub, we've upgraded from a standard off-the-shelf Ethernet cable to a Blue Robotics Fathom tether. We've also upgraded from Fisher connectors to Subcon 8-pin Ethernet connectors. This tether upgrade provides a more reliable hardware connection with their sub for testing, debugging, and surveying. A custom topside box, including a dual radio Wi-Fi router with wireless client mode, allows us to create a wireless network for laptops to connect to the sub. It also provides internet access to all devices on the network when in the presence of an internet-connected Wi-Fi signal. On board, we use a combination of RS-232 and USB to connect to peripherals.
Hello, my name is Advait Sethuraman. I am a rising senior at Carnegie Mellon University studying electrical and computer engineering. This is my first year on Tartan AUV as the software lead. My focus is mainly on computer vision and state estimation tasks. This year, we added new sensors that will greatly increase our ability to navigate and perceive the environment. We currently use an inertial measurement unit, a depth sensor, and a Doppler velocity logger for state estimation. We have dual stereo cameras for visual perception and a rotating sonar for new detection algorithms in the future. As our mechanical team was designing and building the new chassis, the software team developed in the simulator. We use UUV simulator in Gazebo to provide an environment to test our localization, perception, and controls software. This allowed us to develop software in parallel without being bottlenecked by the physical hardware. The simulated robot has simulated sensors, so all we need to do when switching to real hardware is load our sensor drivers. Our object detection pipeline is called the detector bucket. Each detector reports a detection to the bucket in a server-client configuration. The bucket will spawn a detector daemon, which is a submodule that keeps track of the detector's detections. This is abstracted in this way to allow specialized trackers or algorithms for various sensors. For example, tracking for sonar or hydrophones may be different from tracking for visual input. Our detection pipeline is a lightweight and flexible system, which will allow for future sensors and new algorithms. Here is an example of detections from our cameras, localized in 3D space and filtered by dedicated Kalman filters for each detector. We use a deep neural network for object detection, along with classical algorithms for detecting objects like the gate. Each detector daemon reports new detections for each time frame to the SLAM backend system. The measurements are then incorporated into localization. An important problem to solve is one of data association. Given a detection, how do you know if it is a new object or an object you have seen before? This also helps with filtering out false positives from the detectors. Our data association system can be expanded on in the future, but for now, we use the Mahalanobis distance as a scoring metric and a linear assignment algorithm called the Hungarian algorithm for efficient matching. Other algorithms were considered, such as the joint compatibility branch and bound algorithm, but we decided to keep it simple and expand in the future. Our detection system is configurable and is able to use any prior knowledge we have about the objects it wishes to detect. The dimensions of objects are very useful because they can provide us with realistic bounding boxes with which we can inform our path planning algorithms. The scale of objects also helps in detections like the gate, where we can completely localize it in 3D using simple geometric relationships. Perceiving the world in 3D will allow us to execute more complicated maneuvers and interact more intelligently with the environment.
We use a hierarchical, nonlinear, model-based control system for Kingfisher. At the low level, we have a differentially flat model of our sub, featuring flat outputs corresponding to the x, y, z position, as well as heading and their derivatives. A low-level PID controller stabilizes the roll and pitch axes for attitude control. A custom linear model predictive controller, or MPC controller, is used for trajectory tracking. The MPC controller is based on the OSQP quadratic programming library and provides a 2-second horizon along which it can predict and optimize the control inputs for the vehicle.
Hi, my name is Vishap Jain. I'm a rising junior studying electrical and computer engineering. This is my second year on Tartan AUV as part of the software team. I worked on our computer vision detectors and also helped structure our budget and develop corporate relationships. Sponsorships from our corporate partners are crucial for our success and growth of our program. This year, we were able to make major capital investments in our navigation sensors with the support from our sponsors. In addition, Carnegie Mellon's Robotics Club supports us with access to fabrication equipment and financial management.
While unfortunately we weren't able to represent them at competition this year, I want to take a moment to thank our incredibly generous sponsors. Our gold sponsors included Leidos, who generously provided the funding necessary to purchase a Doppler velocity log, as well as the Carnegie Mellon University Student Activities Fee and Altium Designer. Our silver sponsors included Blue Origin, Blue Trail Engineering, and the CMU Robotics Institute,
as well as Exits.
and our bronze sponsors, including Molex, NVIDIA, IMC, Connect-Tech, Advanced Circuits, and the Robot Perception Lab. Thank you. Overall, we're incredibly proud of the progress we've made on Kingfisher this year, and we can't wait to see where it goes in the coming years.